All right, guys, this is section 4.4, the shapes of molecules. So it's kind of important for you to follow along with the geometry handout sheet from your packet. Near the end of your packet, it shows different shapes and their names, and it also shows the geometry of those um, angles in the shape. So you can need that to follow along. All right, so we should all know that molecules are not two-dimensional. Um, we're in a 3D world, so angles are not going to be 90 degrees and or 180 or stuff like that in these shapes. We will get to some shapes that have 90 and 180, but you can see in methane it's not 90 degrees. So please do not ever use 90 degrees for a tetrahedral shape. All right. They actually are 3D. So in methane itself, or any tetrahedral shape, you're looking at 109.5 degrees is the bond angle between the outside atoms and the central atom of carbon. These are covalent bonds, so you can see that they're sharing electrons. And what happens when you start sharing and you have lone pairs is that the bond angle starts to shrink. So for example, water, these pairs up top are going to push around and lower the angle to 104.5 degrees. So these unpaired electrons are repelling each other, so it kind of pushes the bond angle closer. So you're looking for electron pairs, bonded and lone. The ones that are lone are going to repel each other. The shape is influenced by the number of pairs and unpairs. And the strength of the repulsion, the lone pair is greater than a lone bond and even greater than a bond. So when they are, the more lone pairs you have, the greater repulsion. It causes the angle to shrink. All right, no repulsion. So you can see in methane is 109.5. There's no lone pairs. Add one lone pair like ammonia, the bond angle shrinks to 107. And then if you have two lone pairs in water, so oxygen has two lone pairs, it shrinks even more to 104.5 degrees. These are estimates and they're not exactly perfect, but it's an average of 104.5. So more lone pairs causes the bond angle to be reduced. So this is your geometry chart. Helps you memorize, or helps you identify the shape and the bond angle. You won't be able to use this on like the ACE exam, so it's nice to have it memorized. So you can see the different shapes that the linear geometry has, the trigonal planar has, the tetrahedral has, and then you can see the bond angles shrinking, for example, between a tetrahedral, trigonal, pyramidal, and a bent. And then the other ones are more complicated because there's more atoms. You have the trigonal bipyramidal and the octahedral group. All right, so here are some other examples. So a linear one is an example of CO2. There's two bonding sites. There's no lone pairs. Trigonal planar has 3 domains, but no lone pairs. So it makes a plane of 120 degrees. And then you also can have 3, but with 1 lone pair, for example, a nitrite ion, NO2, causes a bent shape with a lone pair. And so forth. You can see tetrahedral again has 4 bonding pairs, no lone. Trigonal pyramidal has 3 bonding pairs, 1 lone. A bent has 2 bonding and 2 lone. Okay. And then the same thing with 5 domains and 6 domains. So how do you determine the shape? You must correctly have the formula. So you have to know the formula. You have to develop the dot cross of the compound. That's why we did that first. and then you count the number of pairs and lone pairs around the central atom. So for example, F2O, oxygen is the central atom. It has a bond with fluorine sharing a covalent bond here and a covalent bond here. It has 4 total pairs. You have 1 pair, 2 pair, 3 pair, 4 pair around oxygen, 2 lone, and 2 paired. Okay, so the 2 pairs are with fluorine, the 2 lones are obviously alone with oxygen. So you go to your chart, you look for 2, or a total of 4 pairs, 2 lone pairs, and you connect the lines so you know that it is bent at 104.5 degrees. So you have to know the total pairs and the total lone pairs, and that will tell you your shape using the chart. Bent shape with 104.5. All right, predict the shapes and angles for the following molecules. We have CCl4, so it's a good time to pause, try it out for yourself, or you can follow along. Here's carbon tetrachloride. So we have 4 total pairs. We have no lone pairs. So 4 gets circled. Oops, sorry. And we have, it should be a tetrahedral shape. Sorry about that. Second one, beryllium chloride, again, has 2 pairs, no lone, so it's linear. And then PCl3 has 3 pairs, 1 lone, so 4, and then the 1 goes to trigonal pyramidal, 107 degrees. All right, electron deficiency. This also follows the same pattern, but boron is always going to have 6 electrons most of the time. It has 3 bonding pairs, and they form a bond angle 120 because it is a triangle that's broken up in thirds, and that's 360 divided by 3 is 120. So you can see here, boron having 6 electrons, 3 pairs, no lone. Sulfur hexafluoride, okay, has 6 bonding pairs, no lone pair, so it's an octahedral. This one, the shape is 90, all the way around. Basically makes a square in the middle, and then you have a 1 up fluorine, 1 down fluorine, and all of these are 90 degrees. So you can see here, it's called octahedral because it's 8 sides, 4 on the top, 4 on the bottom. It's kind of like a diamond. So, sure, I get it. Electrons share to make covalent bonds. So how does this go back to the previous chapter of orbitals? So what's happening in these molecules and what's happening to the orbitals, since electrons are affecting the bond, so the orbitals have to be changing. So this is where it gets a little difficult. So this is where put your thinking cap on. So here we have carbon. 1s2, 2s2, 2p2, 6 electrons. So nothing happens to the 1s. That's the one thing you have to forget about because it's not the valence electrons. So carbon has 4 valence electrons. That means there's 4 bonding sites. So for 4 bonding sites to occur, that 2s has to change, and it forms into a hybridized shell, hybridized orbital. So the 2s, 1 electron jumps to the 2p, so now you have all lone electrons. So they're all 4 bonding sites, but they form a hybridized orbital. It's called a sp3. It's called sp3 because it has 4 bonding sites, the 1s and then the 3 p's. So 1 plus 3 is 4. So what happens is it's exactly what a hybrid means. It takes 2 of the orbitals and they merge into a hybrid. So carbon gets excited to bond. Yay, bonding, yes. which causes electrons to move. That's why it goes from a 2s, one of the 2s to a 2p, and then all these orbitals will hybridize into one. So these atomic orbitals that overlap, they allow electrons to be shared now and form 4 bonding sites. So each one of these electrons will bring in an electron to share to form a covalent compound. And that's how these orbitals interact and make the bonds. So they have to hybridize first, and then they allow bonding sites to occur. Right. So combined orbitals are called hybridized or molecular orbitals. So they're hybrid because they're merging two type of orbitals together. The amount of overlap determines the strength of the bond. So the more overlap, the stronger the bond. So these are your types of possible bonds. These are your sigma bonds. So sigma bonds can form in just 2 sigmas back to forth, back and back, like a H2, hydrogen, diatomic hydrogen. It's only the S, so the only S gets hybridized. When you start in the p orbitals, you can have the S from hydrogen and the P from carbon that can overlap. And then if you have p orbitals that are overlapping, that's a stronger one. They will form a sigma bond too. So I always think of sigma equals single. If a single bond forms, there's a sigma bond. SS. All right, so let's look at ammonia. So if you remember, ammonia has only 3 valence electrons for nitrogen. So the hybridization of it, okay, the 2s, one of these electrons will hybridize, or these electrons will hybridize into the sp3 orbital or hybrid orbital, and then it only has 3 bonding sites. So you can see here, 1, 2, and 3 sites where nitrogen can bond. So even though there's a lone pair, there's no bonding, it's still a shared electron that is, still a hybridized electron shell. So same hybridization for nitrogen as in carbon, except there's only 3 bonding sites. So even though there are 3 bonds, it still contains sp3 hybridization, because that's the outer electrons of nitrogen. So the same thing happens with water, H2O. So in H2O, oxygen has only 2 valence electrons that are free, but the S and the P are going to hybridize into the same hybridization of sp3. So basically, if it has 4 pairs tetrahedral, it's going to be sp3. So 1, 2 bonding sites for oxygen. That's why the formula is H2O. So 2 bonding sites, 4 hybrid orbitals. All right, you look at boron. So boron has 3 valence electrons, okay? And when it hybridizes, it only has 3 bonding sites. So the hybridization is just sp2. 1 in the S, 2 in the P, 2 plus 1 is 3. So it's a total of 3 bonding sites for boron. No lone pairs, so the hybridization is sp2. So since it only has 3 valence electrons, it can only hybridize 3 bonding sites. So it can only be sp2. dsp3 hybridization, so like phosphorus can hold more than 8 electrons, can hold 10. So there's 5 bonding sites. So that means the D has to come into play because there's only 3 orbitals in P. So the D comes in, so it's dsp3 or sp3d. You can put the D in the front or at the end. So that shows 5 bonding sites. 1D, 1S, 3P, that's 1 plus 1 plus 3 is 5. So basically, if it has bonding sites or lone pairs, you're going to hybridize. So phosphorus has 5 valence electrons, and you can break the octet rule, which means there's 5 bonding sites that hybridize. And the reason why I can do that, because the third energy level contains the d orbital. All right, more stuff. Sigma and pi bonds. So sigma bonds are single bonds, sigma and single. Now what happens when you start interacting with the other p orbitals, x and the y lobes? If you're talking about pz, it could be either one. Okay, so these are your sigma bonds. So you have the z, in this case, are forming with a sigma bond, ZZ. Okay. Erase that. Erase that. So pi bonds occur between the px and the py lobes, the ones that form double and triple bonds. So in this case, you can see the sigma bond forming here between the carbons, and then you have a pi bond here occurring with the p orbital. Okay. So this is where it gets tricky. Pi bonds don't hybridize. Okay, only sigma bonds. So in a pi bond, it's strictly just p orbitals. So the p orbital doesn't do anything. It doesn't hybridize in this case. So in alkenes, the carbon double bond, you have the same configuration for carbon here. When it hybridizes, it forms the s and the p and 1 electron each. But one of the p orbitals does not hybridize because it forms a double bond. So that leaves you with 3 hybridized shells, which means it's sp2. 1 for the s, 2 for the p, gives you 3. Okay, so you can see here the double bond in ethene. You have the p orbitals that are not hybridized, that forms a double bond. And then in the middle is your sigma bond that is hybridized. Very tricky. So you look at a triple bond. Again, the carbon atom has 4 valence electrons. It hybridizes into 1 each in the orbital. But since there's more electrons forming that need to form, 2 of them aren't going to be hybridized. So the 2 of the p orbitals don't change, but the only ones that change are the sigma bonds occurring between hydrogen and carbon itself. So there's only 2 bonding sites for a triple bond, and that means there's 2 hybrid orbitals, 1 for s, 1 for p. So a triple bond has, again, the sigma bond first, that forms always, and then the p orbitals that aren't hybridized in orange, that's where the double and triple bond occurs. So one bond in the py and the other one in this case the px, or pz, sorry. So these are hybridized. The ones are in blue, the one bond between the H and the carbon and the other one between the carbons. And then the orange ones are not hybridized. Those are forming the double and triple bond p orbital, pi bonds. Okay. So what happens in organic molecules? The same rule applies. Look at how many bonding there are. There are 4 bonds in ethane. So 4 bonds, all sigma. That means it's going to be tetrahedral group. There's no lone pairs, so it's going to be 109.5. Okay. Ethene, on the other hand, has 1 pi bond right here forming, that's not hybridized. So if you look at the geometry, if you have three bonds pairs, no lone pairs, it's going to be a trigonal planar, which is 120 degrees. Okay, so you can see the pi bonds are forming in green and the sigma bonds in orange in this case. Now ethyne, again, only has two bonds between one of the carbons and no lone pairs. So two bonds, no lone pairs is a linear shape, which is 180 degrees for ethyne because it forms a triple bond. So I'm sure there's going to be questions, and this will be more elaborate in class and a little more easier to describe again for the second time. So please ask, and thanks.